Ideal gases. The kinetic theory of ideal gases takes 5 main assumptions. 1, that the size of molecules is negligible compared with the mean intermolecular distance. Inter and intramolecular is going to be very important. Intermolecular means between the molecules. Inter, I-N-T-E-R, would mean between. Intra, I-N-T-R-A, is within. So we're talking about intermolecular, so we're talking about the distance between them. Assumption 2, that the molecules move with different speeds and in random directions. Assumption 3, standard laws of motion apply. Gravity still applies to gases. They are still pulled down, they have very low mass, but gravity still applies. Heavy gases can still be held within a cup without a lid. They're still pulled down in a direction towards the gravity and held in the bottom of a cup. Collisions between molecules are elastic, which means that the kinetic energy is not converted into other forms. So when we're talking about elastic, think of a rubber band. They're hitting each other and ricocheting off. Okay, so they do not change that kinetic energy into potential energy. Whenever you hit someone else, normally one of you stops. That kinetic energy is transferred. However, with these gas molecules, they're moving at such rapid motion that when they do collide, it's supposed to be elastic. Therefore, they bounce off one another, just transferring kinetic energy. And there are no attractive intermolecular forces between molecules except during collision. So these are our assumptions. So no attractive forces, meaning that these molecules get near one another and it doesn't actually change their direction at all. Now, 2 of these assumptions don't always apply to real gases. These are ideal gases. These assumptions make our calculations very simple, but they are not always applying. So our limitations are assumption 1. Real gases do have a volume. Now, when we're talking about just air in the room around us, those molecules are spread out so far from one another, the size of them compared to the space between them, we can call it negligible. The problem is these assumptions don't always apply. When we start talking about large gas molecules, their volume starts to matter. The amount of space they take up, especially if we start condensing them closer and closer to one another. Remember, the only difference between a liquid and a gas is how condensed the molecules are. In a liquid, they're condensed to a set volume. In a gas, they're not. In a gas, they've now expanded to fill whatever volume they're at. But as we cool a gas, we cool it down to a liquid. There is a point where it is still a gas, but really close to being a liquid. It definitely has measurable volume at that point. Now, these small molecules, in general, they don't deviate very far from this ideal theory. So what happens is if the gas particles have a significant size compared to the total volume, the volume of the remaining space in the container is reduced. Therefore, the effective gas volume is reduced. Now, assumption 5 is also incorrect. Intermolecular forces of attraction do exist. Assumption 5 said that there are no intermolecular forces, but they do exist. And when these molecules go near one another, those forces do have an effect. Now, the 2 of these combined come down to the fact that real gases deviate from ideal behavior at low temperature and high pressure. So because the real gases deviate at low temperatures and high pressure, we can think of an analogy. Okay, if I'm talking about intermolecular forces, we're talking about these forces of attraction between molecules. So we're talking about this hot girl and this hot guy walking near one another. Do they notice each other and stop in their path or not? Okay? If they're at low temperatures, then they're moving slow. If you're moving slow, you're more likely to notice someone. If you are running, you're less likely to notice anyone. But if you are moving real slow, you're looking around, right? So if these gas molecules are moving really slow, they're at low temperatures, they're much more likely to slowly pass one another, and those intermolecular forces are more likely to attract one another. Also, if they're at high pressure, that means they're really close together. If hot girl and hot guy are at two ends of a football field, they're not going to notice one another, no matter how slow they're going. But if they're at a high pressure, meaning they're really condensed together, they're all in one room together, and they're moving slow, they're really likely to notice one another. These are our gas molecules. Okay, the intermolecular forces is literally the force of positive and negative attraction pulling these molecules together. So when are they more likely to get pulled together, get pulled off track? If they're going in a straight line and that positive and negative force pulls them away, they're going to be moving slower, and they're going to have to be a lot closer to one another. So when we're talking about the difference between real and ideal, we need to think about our high temperature and low pressure is our ideal gases. Because at high temperature, they're moving really, really fast. All those assumptions work. At low pressure, they're really, really far away. All the assumptions work. So whenever we get away from these assumptions, whenever we are at low temperature and high pressure, and now we're talking about real gases where our ideal gas law doesn't really come out right, there is a way to calculate that. That's called van der Waals equation. We will not be using that in this course, but it does give you a visual representation of how the difference is. So I want you to watch the Crash Course Chemistry over Real Gases. I've linked it on Edmodo. It's like 11 minutes. Watch it at 1.5 speed. Make it down to like 7.5 minutes. It's very good. It gives you some really good visuals of what I'm talking about when I'm talking about a visual representation of an ideal gas where all of our ideal gas law calculations are accurate versus a real gas. When I'm talking about a really condensed gas, all of a sudden my calculations don't work anymore. So if I take the air that's in a regular balloon and I condense it down to the size of a ping pong ball, my ideal gas law equation is not going to work anymore. I've made it so condensed. All these molecules are so close to one another. The assumptions of the ideal gas law are no longer accurate, and that needs to be calculated in an entirely different way. For this course, what you need to be able to do with real versus ideal is explain results based off of real or ideal. You'll never have to calculate the differences here. But if you get results and you're said, okay, now what makes you think that this follows the ideal gas law, or what makes you think that this would deviate from ideal gas law? You need to be able to keep this phrase very much in mind and be able to explain it. At low temperatures, they are very close to one another, and at high pressure, they are very close to one another. They're moving slowly and they're close to one another. They're more likely to interact, and those ideal gas behaviors are less likely to happen. A visual representation for that would apply here. As pressure increases, we see this change in gases. Okay, if we have PV equals nRT, if we have a constant of our ideal gas law, each gas at certain points fall into this ideal gas law. But every gas deviates, especially based off of their sizes. Okay, the larger the gas, the more the deviation. All right, ideal gas law. On the AP test, if you look at your formula sheet, you are given the ideal gas law, you are given Dalton's law, you are given the R constants with all the units, and you are given Celsius to Kelvin transition and ATM to millimeters of mercury to torr. All of those conversions are all given to you. What are not given to you are Boyle's law, Avogadro's law, and Charles' law are not given to you because you don't need them. They are what combine together to make the ideal gas law, PV equals nRT. Now, Boyle's law, Charles' law, and Avogadro's law, we're talking about change over time. So if I want to make that equation happen, then instead of PV equals nRT, then I have P1 V1 over N1 R1 T1 equals P2 V2 over N2 R2 T2. Cancel everything that stays constant in that current equation. So if I have R, which is always a constant, well, that is always going to cancel. So you never have to have R on both sides. Now, based off of the problem, does it say moles change? If moles don't change, then N's constant. You get rid of it. So if I have a problem and it says that our moles are constant and our temperature is constant, that would get rid of N and T, which would just be P1 V1 equals P2 V2. also known as Boyle's law. Okay? If I have one that says that my pressure is the same and temperature is the same, now all I have is V1 over N1 equals V2 over T2, Avogadro's law. Now, effusion versus diffusion. Diffusion is the movement of gaseous particles from one place to another, usually from an area of high concentration to an area of low concentration. The burnt popcorn in the back corner has diffused over to my nose. Why? Because they're gas molecules. They're bouncing off of one another, and the way that that would work is if I bounce off, I will go in a random direction. That just makes diffusion happen. That's why diffusion always happens. These gas molecules are in constant and random motion. So if they're in high concentration, they're bouncing off of one another and shooting each other in off directions, away from the high concentration, therefore it diffuses away. Effusion is the escape of a gas through a tiny hole. So the open door in the back of the classroom, gas is effusing through there, effusing through it. It is escaping through a small hole. Now, who goes through the small hole faster, small molecules or large molecules? Small. So with effusion, when you're asked a question about which would effuse quicker, it's who's small, who fits through the door faster. Gaseous particles are constantly moving with random motion. This is what leads to this diffusion. Gaseous particles undergo diffusion because of their kinetic energy. Gaseous particles tend to leach out through small holes through a process called effusion, and the effusion rate of a gas is inversely proportional to the square root of the mass of its particles. In other words, big move slow, small move fast. That's effusion. Now for our demos.